Amazing. Okay, well, it looks like it's running without any problems. Whew. All right. Hey, everybody. Welcome to lecture 4 of CMSC389E. Today is multipliers and iterative algorithms. Right on. So, getting started here, project submission. I think what we will do today is talk a little bit about it at the end of the presentation. So stick around for that, or if you're watching the webcast, I guess you can just fast forward to the end, but that's where that'll be. Course website has yet to be updated for this week's stuff, so keep your eyes peeled. That'll probably happen sometime over the weekend. And real quick, has anybody had any issues with the Elms itself, like accessing it or using it, anything like that? I guess just now's the time to like drop it in chat or something, and we can sort of figure it out. But if you can if the Elms page shows up and you can see the assignments pop up, that should be good. So can anybody not see those? Sweet. Okay, we're still in the process of getting the submit working. It's kind of slow to move anything to the CS department, but we do have that at priority one. So we'll talk a little bit about that later. But that's all we've got for this sort of announcements business. Okay. So project 3 really just involves more adders. Project spec will be kind of coming out soon. Will be on the Elms and the course website imminently. And also, I just wanted to add, projects are becoming slightly more involved, right? You'll find they kind of peak in difficulty around the middle of the semester, and then they'll kind of mellow out. As this happens, feel free to schedule office hours with us via Discord. Both of us, me and Ashwath, are open to it via appointment. And we have, the Discord here. We used to do it last semester as well through Discord, and it worked pretty great. So if you do want some time, if you can't figure something out, or if you just want to go over how to build a certain thing, that's totally valid, right? To arrange office hours. So make sure to ping us on Discord if you do want to do that, or if you're more comfortable with sending us a direct message, go ahead and do that. Either one of us should work. And we probably both have slightly different availability, so for your best chances, just ping both of us, and we'll coordinate and figure something out. So just wanted to make sure you keep that in mind as the projects get a little tougher. You're not in this alone. Also, we do have a policy about group projects. I think as long as you let us know like 4 days before the deadline that you will be working on a project in a group, you are allowed to complete these projects as groups. So that applies to all the projects that we've got.
And just to clarify, for when we say group projects, everyone still has to turn it in, but you'd have to tell us beforehand who you're working with.
Yes, great point. Yeah, everybody still has to turn in a file. That's just so, we don't get, well, anyway, yes, everybody does have to turn in a file. So make sure you do, regardless of whether or not you're working in a group, turn in a project file for the project that you're doing. Cool. All right, we'll go ahead and get started today with multipliers. And I just want to start off with kind of a similar line of inquiry that we had last time, right? So we worked with numbers last time. We talked about number representation in binary and all that, and adders, more importantly, in addition, right? So now we want to know, how does multiplication work in digital circuits, right? Simple question. And my answer for you would be, first we have to ask how multiplication works in binary, right? That's the real question we should be asking, because that's how we kind of went through figuring out how addition worked. So we're going to do the same thing for multiplication, right? Along the same lines of just figuring out arithmetic here. So consider multiplication in base 10, right? I want you to think of how you do multiplication on paper, by hand, or just regularly in base 10. The real goal here is to think of the analog of that, but in binary, right? So single digit multiplication in base 10, let's talk about that. You have, any option from 0 times 0 up to 9 times 9, right? You can have 1 times 2, 3 times 4. We're basically taking any single digit decimal number and multiplying it by another single digit decimal number, right? You'll notice that we're doing the sort of same thing here that we did with adders, where we first decided to add 2 single digit numbers, binary numbers, and we came out with a solution. Same deal here. We're going to attempt to multiply 2 single digit binary numbers and come out with an answer here. So following that line of logic, right, it's actually a lot easier. Whereas base 10 multiplication single digit would go from 0 times 0 to 9 times 9. Binary multiplication with a single digit would only be from 0 times 0 to 1 times 1. right? And that's because we only have 2 options here, whereas in the decimal number system we have 10. So that's good to know. And don't actually overthink it. This is the entire times table for single digit binary, right? It's pretty simple stuff. 0 times 0 is 0, 1 times 0 is 0, and 1 times 1 is 1. In fact, you'll see that this entire thing can be represented with just a single logic gate. So I mean, if it's like not immediately apparent, just give it a second and just think about it. And you can see that we can actually represent single digit multiplication in binary with a single logic gate, right? So again, if you take a look, it looks kind of like a truth table, right? You can kind of make that connection. And it ends up that we just, we use an AND gate, right, to represent multiplication of a single digit. So what does this mean for us? That was pretty easy, right? Does that mean our multiplier can just be an AND gate? Unfortunately not, right? This is just the tip of the iceberg in this sense. We need to handle n-digit multiplication. In other words, we need to be able to take as many digits as possible and multiply them, by as many digits as possible. So we need a sort of general solution to this. This single-digit business won't work for us. So again, let's take a look at the long method of doing this computation, for some inspiration, just like we did with the addition, right? So we're gonna sort of take what we know already, or doing our math by hand, and try and turn that into a more computerized digital way of doing it, right? So let's go ahead and take a look. We start off with this, right? And I want you to first note how we're doing this. It's the same way as we'd be doing multiplication in a decimal form, but it's important to take note that we're doing this. Oh, I seem to have okay, that's gone. Excellent. So we seem to have the same sort of system that we do with decimal multiplication, right? You can see here that over here 1 is a product of 1 and 1, 0 is a product of 1 and 0, 1 is a product of 1 and 1, and 1 is a product of 1 and 1. So you notice this first row right here comes out the exact same way as we would if we multiplied decimal numbers, right? So no problem there. We're doing this the same way we'd start off long multiplication by hand with decimals, right? But it gets a little tricky as we move forward. We'll go ahead and see that. But the rest of the multiplication works the exact same way. So if you'll recall, I don't know, it's been a really long time since I've done multiplication by hand. But you want to add that trailing 0 at the end, right, when you perform the second computation. And now we're moving on to this second one from the right side. Same deal, right? We're just multiplying 1, and you'll notice right off the bat that this computation is very straightforward and easy, right? If you have a 1 times 1, you get a 1. Otherwise, in any other case, you're going to come out with a 0 in whatever spot you have, right? And so if we continue adding those trailing zeros and we perform the multiplication as we usually would, you'll notice we keep getting, these exactly what you'd expect, right? And that goes on all the way up until we perform all 4 digits of this multiplication, right? And now I want you to notice something here. Once we have all of this, in regular by hand multiplication, what we would do at this point in time, at this juncture, is just add all of them up and produce a solution, right? And it turns out we do the exact same thing here. So we end up with something like this, right? And the way this is computed, I want everybody to kind of make sure they understand how this end result is computed, right? Because this is sort of the bread and butter of how multiplication works here. And that is, it's just a series of adding, right? So here we see that 1 comes out to 1, 1 comes out to 1 here, 1 comes out to 1 here. So these first 3 columns are pretty straightforward. We just have 1s and 0s, but I want you to make sure you understand how carries work, right? So I made this example this way on purpose. Take a look here. We have 1 plus 1 plus 0 plus 1, right? Let's talk about how that would work in binary. So 1 plus 1, let's think of that as rolling back over to 0, right? Because in binary, we don't just come down here and say, oh, that's 3, right? It's almost like in decimal addition when you have, like 5 plus 5. That rolls over, right? That rolls over to 10, so you need a carry over. So similarly here, 1 plus 1 will give us a carry of 1 and put us back at 0 here. But look at that, we've got another 1. So really what our result here for this column, this particular column that I'm mousing over, is 1 with a carry of 1, right? So let's make sure we get that. Again, if anybody has any questions, just drop it in lecture questions. Let me make sure I have that window popped up here so we don't get lost. Yeah. So that's the kind of deal there, right? We want to make sure that we know that this comes out to 1 with a carry of 1. And over here, now that we have a carry of 1 and 1, our solution is 0, right? This comes out to 0, but we still have a carry of 1. That carry of 1 comes out here. We get another 0, again with a carry of 1. We get another 0, again with a carry of 1. That's how that kind of comes out, right? So again, how do we handle carries greater than 1? Excellent. That is actually the next slide. So it's a great point, Pars. So this is how we'd handle it ourselves, right? Carries greater than 1. Excuse me. Carries greater than 1, we have like a little bit of an issue, right? When we handle something like this, especially when we get to digital logic circuits, right? So moving forward, let me just get through this one bit first, then we'll talk about carries greater than 1. What does this tell us about the multiplication in this case, right? Well, it tells us it's easier than decimal, and also the same thing as we do with decimal. We go from right to left, multiplying the numbers. The big question is, well, see, multiplication is actually just a lot of addition. I think since this is a university class, I'm supposed to tell you that Nelson Mandela didn't actually say that. But multiplication is essentially just a lot of sequential addition, as we saw here, right? So going back to this, it really just is a bunch of adds, right? And again, handling carries greater than 1 is a little bit tough for us, right? Again, it's not so bad when you consider that you can just compound all of those carries and keep moving them and propagating them forward, right? Until you finally, so if we had like maybe another carry 1 leading into here, all we'd do is just add a 0 and then a 1 here, right? But really, we need to talk about how a circuit would handle that, because that's our real concern, right? So that's a very real concern. And I want us to stay on the idea that multiplication is really just a lot of addition, moves together, all happening in one row, right? So knowing that, the key word here is sequential, right? We're going to leverage that in terms of producing results for how we multiply, right? And it turns out there is a way to leverage that system such that we can handle carries of any amount, right? So let's talk about that. Remember, we already know how to add, and the fact that we can do this sequentially is good, right? This tells us we can have adders after adders to achieve sequentiality. Again, notice that right here, what I'm trying to say is this operation here does not have to happen like concurrently or anything, right? It can happen sequentially. In other words, we can kind of add all of these numbers at our own pace, right? We don't have to go all in one go. We can add them at our own pace, and all we have to do is eventually come out to this binary number. That's good. So you should kind of be thinking about how, even though we're multiplying up here, really what we're doing is adding just a heck of a lot more numbers than we would if we just had an adder, right? So keep thinking about that. This tells us we can just use adders after adders to achieve sequentiality. So that's our first hint as to how we'd construct something like this, right? Once we've got that in our heads, let's talk about implementing multiplication. So really what we're going to be doing here is leveraging full adders over and over, and using them to easily perform repeated additions, right? Additions over and over again in order to produce our result. So let's take a look at how we turn this into a set of adders, right? So not a problem. Let's throw all these into a full adder or something, right? What would be the issues with an implementation like this? Well, if you can think of one, just kind of like float around in your head, or you can say it in chat. Like, how would we? Again, Paras actually came out with the biggest one here. But really, that's just about the thing, right? So what if we have a carry of more than just 1? And by the way, I want to emphasize that it's a carry of more than just 1, not a sum. Remember, we will never have a sum of more than just 1. And make sure you remember that, right? At first glance, you might think, well, we can have a sum of greater than 1. What if we have like 1, 1, 1, 1, right? So even here, right here, you're never going to have a sum of greater than 1. Why? Because when we have a carry, right, that like an overflow, it'll overflow into the carry bit, right? So in other words, this is going to alternate between 1 and 0 based on what's in the column here that's going to be added. So to clarify, we will never have a sum bit of more than 1 because that's not how we've designed this. However, we do want to make sure that we don't have a carry of more than just 1, because we can't handle that with our adders so far, and I don't want to go back and change how our adders handle it. Luckily, there is a way to deal with this, right? The solution here is, well, again, just like Paras said, right, just to sort of rectify the example that he made, suppose we have a column which contains 4 or more 1s. We would have 2 carry bits, right? Imagine if we had one of these columns here, we had 4 1s. That's totally viable. That could totally happen, right? An example of where that would happen is if we had 1 1 1 1 times 1 1 1 1. That's valid. We would get something like that, right? So it becomes apparent to us that doing all of this addition all together in one go might not be the most feasible way to deal with this problem. which is where the sequentiality comes in, right? So again, does anybody have any questions on that? How we kind of got there, right? The 4 carries, so it's 4 1 bits, which comes out to 2 carry bits. Anybody confused about that? We can kind of dwell on that for a second and move on. Everybody all good? Okay, good. Just making sure everybody's got it. Right, so what happens when we have a more than 1 carry bit kind of held out on you for long enough? So let's talk about it. The answer is we're screwed. We can't we can't deal with it. At least in this one format, right? So we're gonna have to come up with a way to sort of combat this and build out a solution that handles more than 1 carry bit. And in this case, we're kind of cheating. We're saying, well, I really don't want to deal with more than 1 carry bit. So how can we mess with this one big computation such that we will never have a carry of more than 1, right? And the answer here is we're just going to have more adders. Let's talk about that. We will find a workaround so we can never have more than a single carry bit, right? And it turns out it's kind of systematic in the way that we build it. Take a look. We're going to perform partial additions, right? We're going to break up the problem into chunks and then go ahead and solve it. So we do something like this. We'd say, okay, first things first. I want to solve this little block right here. So I throw all that stuff through a full adder, right? You know, we've seen this stuff before, totally fine. And once the solution of that comes out, right, sounds good. Once we have all that added up, you know, we're not going to have any problems throwing that through a full adder. Let's take the result of that and throw it through another full adder, this time adding all this stuff together, right? Of course, I'm not highlighting the trailing zeros here, but obviously we'd keep track of those, right? It's just that once we come up with this bit, we will know the answer for the rest of all the bits. Does that make sense? We're kind of ignoring these trailing zeros in this subsequent computation because we don't need to care about them. They're always going to be zeros by definition of multiplication. So again, we do the first green square right here. We calculate that. Then we take the sum of that, and we go ahead and add that to this, right? This computation. And we'd actually just do the same thing again right here. And that kind of gets us our solution, right? We're simply just doing the addition. Remember, addition can be done in any order, commutatively, right? And distributively. So, well, distributive doesn't really work here, but it's commutatively that I'm talking about. We do this, then we take the sum of that, we add that to this, we take the sum of that, and we add that to our final row. And the solution comes out to the exact same as what we'd expect if we were just to add all of it together in one go, right? So in this way, we are doing all of the additions in separate sort of instances, but we are coming out to the same solution that we would have had we done the addition all in one go. So does that sort of make sense? Again, if you have questions, just feel free to stop me. That's what more or less lecture's for. So that's how we'd handle that, right? Notice that when we do the additions in sort of a partial format, we would never have to deal with carries greater than 1. Just because when you're adding, you know, 2 binary numbers, you're never going to have a carry greater than 1. The most you can add is 1 plus 1, right? So that's good news for us. Okay, I see a typing here. How do we add back in the trailing zeros? Excellent question, right? I think, Brian, this will become a lot more clear to you once we take a look at the actual circuit, right? For now, I want you to think about this. Why we overlap the additions again. Okay, sure. Let me talk about the trailing zeros, then I'll talk about the overlapping additions, Richard. So the trailing zeros, it actually turns out that we don't really need to add them, right? Once we perform this computation here, this 1 plus 0, you know, we're good. The result of that can be like, you know, kind of sent all the way down to here. So we really don't need to do any calculations with these trailing zeros. It's kind of interesting how the result comes out. It's really elegant how the solution presents itself digitally. So we can take a look at the circuit and compare back and forth. But the key here is we don't really need to add them back in because we know that this bit is going to stay the same all the way throughout, right? So that's the kind of deal here. But we should really focus on the sort of sequential solution, right? So can we explain where we overlap the additions again? So the reason we overlap the additions, Richard, is kind of, the diagram might be a little confusing, but really what we're trying to do is we're trying to add these two first, right? And their result, we're trying to add to the next number. So whatever comes out of these two, we're going to add now with this, right? And the reason we only need to add these bits together is because whatever is in these two bits, you know the answers, they're always going to be zeros. So we don't really need to perform any quote-unquote addition on them. And this is to kind of tell us, okay, we used an adder which can take an input of size 1, 2, 3, 4, 5 up here, and down here we used an adder which can also take an input of 1, 2, 3, 4, 5. So in other words, we have a 5-digit adder producing the result up here, but we can also use a 5-digit adder to produce the result down here, right? Does that make sense? That's kind of why I'm putting these green squares the way that they're here. You'll kind of notice that we are always doing a computation of max size 5. 1, 2, 3, 4, 5. Makes sense now? Okay, great, great. And again, the 5 is directly related to this right here. Notice that when we perform the very first, very first two multiplication parts right here, the longest result we can get is one with a carry over here, right? One of 5 digits in size. So if we have adders that can handle 5 digits of stuff, we should be good. Some people might ask about overflow in the left direction. Again, we might need to increase the size of the adder. Yes, that might be. Okay, I was wondering if somebody would come up with a question like that. That is also totally valid. I'm trying to keep it like a little simpler here for this example. But again, you just need to make sure that you're facilitating the size of the numbers that are coming out here, right? Again, remember, we're not going to exceed this because by definition, the addition can only have a carry that comes out to here. So the maximum value you'll have in this column is 1. Cool, and same business going propagating down, right? Notice how here, when we add this column right here, the maximum value we'll have is 1 because the only digit we could have in this column, right, when we do this addition, it could be a 1. Right now it's a 0, but if it were a 1, that is what we would be dealing with, right? We would either have a 0 or a 1 here. Cool. Okay, so so hopefully everybody can see how we will never have an overflow come out of the green box, right? So let's take a look at all the green boxes at once. Notice how in all the green boxes we only have 1 digit, right, in the bottom left corner. It's a solid voice crack. Only 1 digit in the bottom left corner of the boxes, right? That ensures that we will never have a carry that exceeds the 5-digit limit, the size of the green box. And that's happening because we're kind of leveraging the fact that multiplication sort of starts stacking leftwards, right? These zeros are pushing them to the left, but we will never have more than 1 element to add in this leftmost column. So feel free to ask questions. Lecture is not as like super long and verbose as it previously was, just for the purpose of people asking questions. So throw them out there. With the first green box when there's 1, 1, 1, 1, 1, 1, 1. Oh yeah, okay, so good point, right? 1, 1 comes out to 0, 1, 0, 1. In that case, when you have a 1 of an overflow, right? Oh, that's an interesting point.
I think what you're not understanding is since the green box is a full adder, right? You end up with a sum and a carry. So the green box can have a carry out. And we will keep track of that. It'll become more it'll become more apparent once the circuit gets shown.
Yes, good point. Perfect. Yes, yeah. Thanks, Ashwat. I guess, yeah, no, that I totally glossed over that. That's my bad. Yes. It does. And in fact, when you look at the circuit, you'll notice that it does actually compound in. Yes. Great. Perfect. Thanks, Ashwat. That was a much less roundabout way than what I was explaining. Sure. Right on. So that's how we've got that. So let's take a look, right? This is the circuit as it would look in binary, and in digital logic, right? And it's a lot of adders. These little blocks here, they're all adders, right? You'll notice that we've got input A for this adder. Let's take a look at, in particular, input A, input B, we have the carry bit and the sum bit. And you'll notice that, okay, I'm kind of putting it in the same diagonal format as I'm putting in here, but it's kind of neat how that works, right? So you'll notice, just like what Miguel said, we've got carries coming out of these, right? Compounding as well. And you'll notice that that'll just carry into the next stage of the adder. And that kind of is what, at the end of the day, allows us to, I guess it's clear in this example, this green box here, it produces a carry, right, after you add it in this direction. And that's kind of the whole deal here, right? It sort of compounds into the next calculation because whatever sum is happening here, that carry out, so for example, one of these carry outs will be kind of dumped into the next calculation. And that's why it's imperative that we use full adders for a calculation like this, right? The only place where you could ever get away with using a half adder in a multiplication circuit is Actually, can anybody tell me? This is kind of good to think about. Just try and do it in your head. Like, where would a half adder ever be possible in this entire circuit? Where would that not screw us up really bad, right? Think about it. It turns out that we're all good in terms of using. Oh, okay. Oh, Richard's got it. Okay. All right. The very last one. Yeah. So right up here, you'll notice that we don't have a carry in. We don't need it, right? And that's the sort of, well, I guess this diagram is a little bit interesting because it kind of doesn't really give us the full story of what's going on. But yeah, no, that's basically what it is, right? Only when you perform this right here, you will never need a carry in. And it's kind of interesting how here we don't really need carry ins here. We're not adding, right? So don't get misled by all these and consider that none of these need like a carry in, because when we do this addition here, from this calculation onwards, right? From this onwards, we can always have the chance of having a carry in. Or sorry, from this calculation onwards, we can always have the chance of having a carry in. My bad. So you'll notice that after this point and forwards, we could have a 1-1 here, right? Notice that this first addition, we will never have anything greater than 1. Why? Because we have that trailing 0 there. But from this calculation onwards, we always have the opportunity to have a carry in. So perfect, yes. And then moving forward from here, even though there are more trailing zeros, you'll notice that we always have a carry in thanks to the previous addition. So again, what Miguel talked about. Anybody have any questions on how this analog to the longhand multiplication is kind of working? Does that kind of make sense, right? I tried to get a 4x4 multiplier to map over perfectly with the 4x4 multiplication that we're working on. Sweet. All right, so that's multiplication, right, in binary. And again, it's just a bunch of addition, right? It's the same way you kind of think about it in real life. What is multiplication, right? It's just adding stuff over and over. It turns out, same deal in digital logic, right? We're just leveraging the fact that it is indeed adding stuff over and over, and we're coming out with something like this. Okay, so yeah, I guess see the resemblance, right? It's very, very similar in the way that it looks, right? So again, when you're building this, you can kind of get an intuitive feel as to why exactly, this multiplier comes out the way it is. The reason we're focusing so much on the theoretical stuff this time is because I know 250 doesn't explicitly cover it, right, Ashwab? I didn't really pay attention.
With 250, I think this is the first real branch that we've taken from 250.
Perfect. Yes. Okay. Cool. But yeah, that's kind of why we're covering this a little bit more in depth. So generally for this class, if we've covered it in like 250 or 216, I'm probably gonna gloss over the background behind it. But if you want like a review on certain concepts and stuff, we can totally post a video about it or something, or anything like that. So just let us know. Or we could probably just steal some of the discussion material from the classes since we're TAing it and turn that into a little video for you guys. So just whenever. That is all good. Just put in a request. Right. So you can see here, the answers propagate, right? They kind of flow down, which is kind of important, right? It tells us that once we finish doing all of these calculations, right, I want you to take off your mathematics hat and put on your digital logic hat, because we got to think about how all of these calculations will happen, right, in order. And the key here is it's pretty neat. All of these can happen, and they can happen at once. That's fine. But you'll notice that this answer, and this answer, and this answer, and this, once all of these are properly figured out, once all these sums are done, great. Now we can guarantee that the answers coming out of them, the carry and sum bits from this first row, will be all correct, right? And once they are all correct, we can verify that the answers coming out of this row would be all correct. Why? Because they are all being fed in the correct numbers, right? So in that sense, this can happen very sequentially, right? Once all of this is done calculating, all of this can calculate, and once all of this is calculated, this can calculate, and so on and so forth. Obviously, this happens instantaneously, but note that obviously you can't figure out, the answers for this row, let's say, before you figure out the answers for this row. And that's a key here, right? The first set of computations yields the right values for the second set of computations, and so on and so forth. And for that reason, I hope I have it on the next slide here. Oh, okay, perfect. We've got a little graphic here that kind of shows us, okay, yeah, we've got the adds going on. And just like we talked about the zeros, notice the sum here, we're all done. Once that sums up, we can send it all the way down, right? Because the rest are going to be zeros. So remember all the zeros we had, the trailing zeros? That's this empty void right here. Right, so hopefully you can, I'm going to go back to the slides. The key is really just making sure these two are kind of synonymous in your mind, right? Once you know that, you're kind of good to go. And again, if anybody was ever wondering why we ever added those trailing zeros when you multiplied, I guess now you have a sort of digital analog as to why this could potentially be, the quote unquote right way to learn multiplication. I'm no math major, but that is a pretty neat thing to remember. So this is called a combinatorial multiplier, right? It is worth noting that there are other ways to implement multipliers. There's some really snazzy ways to do it. I think it's doable in Minecraft as well. I think actually by accident I implemented a multiplier the wrong way because I didn't want to use a lot of adders. But there are other ways to implement a multiplier. In this class, we're just going to cover combinatorial multipliers because it's 1 credit. So one more little aside here. How do we deal with negatives? We use 2's complement, right? 216 just did that. If you need a review in 2's complement, I can go ahead and make one and post one. Do we have any demand for review on 2's complement? Just go ahead and throw it in like lecture questions. If there's no demand, then I'm gonna. I mean, this is one of those things you could maybe Google or I'd write up something on the textbook at the very minimum. So that's probably what we'll end up doing here. But yeah, just let us know. I think they also cover in 250, maybe. Is it?
I'm not sure if it's mentioned, but mostly the binary stuff doesn't really have to involve 2's complement.
Okay, got you. Okay, cool. Yeah. Either way, you've got it. There are a few nuances involved with that, right? Other than the regular 2's complement business you're familiar with the flipping the bits and the adding one, right? We need to extend the multiplier and the multiplicand before multiplying. Yeah, that's a lot of mult. And the reason we do that is we need these like insurance bits to make sure 2's complement kicks in, right? I think you'll understand a little more when we take a look at this example. So I'm going to flip it over to that. And over here, right now we're doing a multiplication. The best part is when we're using 2's complement, our multiplier works flawlessly, right? With negative numbers, it's sick. It just works, right? And I just kind of want to sort of walk you through this cool example we've got here with negative 15. So again, we're trying to multiply the numbers 3 and negative 5, right? And you'll notice that our maximum, let's talk about the number of bits here. 4 times 4, right? That tells us we could have 4 extra bits of multiply, overflow in binary, right? And that's what we want to sort of represent here. So if we just do the multiplication with the 2's, so again, this is 3, right? But in 2's complement, this is 5. Again, we're assuming that this left bit right here is our sign bit, right? So that's just some 2's complement stuff for you. And when we do this calculation without any additional, scaffolding, right, we come up with some garbage number. This is not negative 15 in any representation, obviously, because we haven't really signaled that, 2's complement is quote unquote going on. Here, if we extend the sign bit, right, we take this 1 and we go brrr, and just spew it all across the left, right? And the reason we do that is to facilitate all these carries that are happening on the left. Because all these carries that are going on the left of our multiplication right here, they need to, also keep in mind that, okay, they are now functioning in 2's complement, right? So they have to deal with the whole flipping the bits and adding 1 and all that business. So you want to make sure that you quote unquote flip the bits for all of these, right? For all the potential carries coming over on the left, you need those flipped bits. So keep that in mind. When you are flipping the bits for 2's complement, you want to make sure you facilitate for all the possible carries as well, right? Again, I can talk a little bit more about that in another video. I don't think we particularly mess with negative numbers a lot in this class, but it's just something cool to note that 2's complement does work perfectly with this. And you can see once we handle that, that insurance bit business, once we extend it all the way to the left, you'll notice that the solution comes out perfectly fine. This in 2's complement, as long as you take the the right side, least significant bits, right? We're working in little endian. We get negative 15. And that's what it is. It just works, right? So 2's complement does work, but if you're going to implement it, make sure you extend the sign bit, right? That's something important to remember when you multiply in binary. Again, I figured I'd touch on this since 250 doesn't cover multiplication, but it's good to note if you are going to mess around with it.
This is good to take note of, especially because Project 4 will have you implement subtraction using your existing adders that you're going to make for Project 2. And so you're going to have to deal with 2's complement a little bit there. And so it's good to have this knowledge.
Perfect point. I think in that case, I will post something about 2, just a little review on 2's complement to make sure people are kind of all on the same page with that. So probably just take something from like 216 material and transpose it onto this class. That should be.
Cool. Sounds good.
Yes. Okay. Cool stuff. So that's just negative numbers and how we deal with them, especially in multiplication. Yes, it was indeed a generation ago. All right, all good. I will indeed post something then. No problem. Cool. So that's how we deal with negative numbers here. Let's talk about limitations, right? Addition, subtraction, and multiplication. We've done it all. So what can't we do? The answer to that question is basically everything else, right? This is a 1 credit class. This is where our Cinderella run sort of stops, right? Division and exponentiation are considerably tougher to accomplish with these small circuits, right? Even some may consider multipliers to be a little bit larger than they, than they could believe is like tasteful. So let's talk about that. First of all, division, right? Let's kind of brainstorm it. Can somebody tell me in the lecture questions chat why would division be so absolutely difficult to perform in binary, right? Just throw it out there in the chat. There is no wrong answer. You could also say it's hard to build. Left to right. Interesting point. Yes, left to right is a consideration, a good consideration, right? That's a good point. We're inversing the multiplication and also the floating point, right? That's the main sort of the main problem that we've got here, floating point numbers. If you'll think back again to 216, anybody remember Larry's long-winded lecture on why you need like 600 bits to represent a floating point number? That's relevant. Yeah, exactly, right? That's relevant stuff. I don't think he's given it at this point this year, but I think it's one of those near the end of the semester things. But let's talk about that, right? Consider floating point number representation, right? Look at how many bits we need to represent a floating point number. That's ridiculous. That's and it turns, and when we perform division, right, we come out with these floating point numbers. And I know what some of you are going to say. When you perform division, why not just handle a remainder, right? Well, it turns out handling a remainder is also a humongous pain, right? Whether you want to, honestly, I think you should be fine. I think once you get it, I don't think he asks questions that are like too tough about floating point numbers. I don't think you have too much to worry about. It's kind of like a neat thing to know. It's like computers only think in ones and zeros, right? So however would you represent a number that's like 3.141592653? Like, there's an interesting way that computers handle representing numbers like that. So no worries. But yeah, I mean, we have no intention of even coming close to representing garbage like this. The Mantissa returns. Yes, absolutely. I already give that a little. How do I? Here we go. I want to give it the little 100 react. I don't know how to do that. All right, I can't find it. That's fine. Oh, perfect.
No, I give it the crab.
Oh, thanks. Beautiful. But yeah, that's the whole deal with division, right? We want to stay away from that. So we're going to stay away from division for now, right? Just keep in mind that it's doable. People have obviously come up with circuits for it. Why? Your 4-function calculator certainly has no problem dividing. But again, that makes our circuits a lot more complex, right? So let's talk about exponentiation, right? Now, if you're familiar with it, exponentiation, you think about it, you're like, well, multiplication is just a lot of addition. What is exponentiation, right? And the answer there is it's a lot more multiplication, but that probably implies that we'd be using just like a crap ton, a metric ton of adders, right? Building that many adders is horrible. It's masochism. This is not an electrical engineering class, so we can't really do that to you guys in good faith. And it turns out that, like I talked about, there are other ways to multiply, right? People have come up with these smarter exponentiation circuits that do the job a lot better. Again, that's kind of outside the scope of what we have in this class, so we can kind of gloss over that. But again, in theory, you know how to exponentiate, right? And there actually is one little way that we'll sort of explore exponentiation as we move on. That could be potentially helpful for us, right? So limitations of the magic that we have so far conducted in this class. Well, exponentiation, right? we can still use adders, um, but we might actually be able to leverage the idea that, remember before when we were performing additions of the same size over and over again? Our big idea is that we want to use adders, right? But what if we were to use adders over and over and over again, right? We had two adders, calculate a result, and then we'd feed the result of those two adders back into the first adder. And we'd kind of go in a loop, right? A loop is a big key word here because that's essentially what people were thinking when they put transistor tubes together and strung up computers all over their walls in like the, I don't know, early 1900s. I actually don't know when computers were invented. But consider this, right? This is what people were sort of thinking when they were putting circuits together, and they were like, well, hold on, we have this computing circuit already. Why don't we just feed stuff back into it, right? In order for it to determine our answers here. And the idea of reusing adders or reusing circuits, saving gates at the cost of speed, right, is where we sort of jump from the cave person, banging rocks together computer science that we're doing in this class, and bridging the gap between that and actual computer science being employed today, right? Think about it this way: that Intel Core or AMD Ryzen or whatever you're running in your laptop, obviously that doesn't have a single circuit to do every computation, right? Realistically, what it does is it does some math, says, okay, I'm all good. Oh, and very nice. That's a nice one. I'm looking to build a PC myself. Um, it does a computation, feeds that out to to cache, to disk, to memory. Again, not context for this class. Um, but it does that calculation, and then maybe takes some numbers from that calculation, feeds it back into the processor, right, and kind of circulates data out and in of itself, and uses the same computing circuits to perform a lot of different math, right? So when we talk about reusing adders, saving gets the cost of speed. Reusing adders, think of that, we're kind of thinking loops, and then you could also think CPU clock cycles, right? Over and over, CPUs will run calculations on the same circuits, but they could be different calculations. And like I said, this is kind of how we're very nice, Rahul. I as well. We kind of bridge the gap between cave person computer science and actual computer science. So I want you to sort of think about this idea, right? I don't think we'll be implementing specifically iterative algorithms in a project, but that is something to keep in mind perhaps for a midterm that would be coming in. I hope you all know we have a midterm. It's not going to be hard, but it exists. I wouldn't worry about it though. This class is generally not very hard to do very well in, so take that as you will. When is it? Excellent question. I will have to ask oh no, I'm my supervisor. Uh, Ashwath and I will definitely figure that out. It is
It's like 2 or 3 weeks down the road.
Yeah, we'll give you fair warning before it. Probably going to give like a poll on how you want the format of that to be. We did Elms last semester. We might do like a printout and like draw on it and send it back, or take a picture with your phone, that sort of thing. Or you could just like take pictures of like you answering it on binder paper. So it's not all gonna be multiple choice. There's gonna be like some multiple choice, some free response, and then hopefully some drawing stuff. Nothing too ridiculous, right? We'll give you all the topics for the midterm.
The material for it stops at what happens next lecture. Like next lecture will be included, but after that, that's where the midterm stops.
Yes, perfect. I'm gonna say material includes everything from L1 all the way to, I think it's L5 multiplexers. So just putting in chat in case people scroll up through it later. Of course. Then all of you guys somebody would say something somewhat insightful, then everybody would just be like, oh yes, I also agree with this person. Clearly.
Going back to when that was a thing, back in like middle school.
Dude, we had like little talking tickets, so I would just like burn both of them at the beginning of the discussion and just say some absolute garbage.
I thought that was a very interesting point, Aki.
Excellent. But yes, so again, iterative algorithms, keep that in mind. It's cool stuff to think about when you think about computer architecture as a whole. So again, this sort of deviates from the, we do have a little bit more to cover. Sorry, I kind of wasted some time there. So we'll kind of go through it quickly. Again, online textbook will have more stuff about this if you really want to look at it. But we will highlight what's needed and what isn't, to kind of do well in the midterm. So don't worry. I do want to talk about cloning in Minecraft a bit because we're going to be building a lot of adders. I was informed by somebody that MC Edit doesn't work for this version of Minecraft, which does not bode well, but we will figure out ways to get cloning easy for you guys to just sit down.
That's an easy fix though. I can just PM Jamie because there's like a blacklisted or like a whitelist of mods. I just feel like the MC Edit is just not on it for some reason.
Oh,
So
gotcha.
we
Okay.
can get that tweaked.
I think so. World Edit should need to be whitelisted, but MC Edit stopped working with like Minecraft 1.13 apparently. So if anybody has gotten it working here, well, first of all, congrats. I have no idea how you did it, but I would really just go with cloning or World Edit. But good point, Ashwat. So we'll get World Edit working. Oh, interesting. Oh, right. Okay. So there's a lot of adders. Hurt my wrist when I built it. That's the point I'm trying to make there, right? So you'll want to use one of the following methods to rapidly replicate structures that you've built, right? Number one, we copy using the built-in clone command, right? So make sure you've created your world with cheats enabled when you're doing this, right? Or you can use world edit to edit your world. We're still kind of working through it, testing it. I was messing with it. Not entirely sure if it's compatible with the mods. We'll see, and we'll make it compatible with the mod to get that easy. But it's good to get practice with the clone command, right? So I would recommend going into one of those super flat worlds, building some random garbage, and trying to like copy paste it left and right, making sure you're doing that properly. But it's important to note that clone in Minecraft is Minecraft's way of dealing with like memory replication. It's like memcopy in C, right? It doesn't really check the recipient memory before dumping your structure into it, which is very rude, frankly. And it's caused problems for me in the past, and I think other 389E students. So keep that in mind, right? Be very careful when you clone structures. If I were you, I'd always clone a backup of whatever you're building to somewhere else and maybe remove the input block so that doesn't cause any problem with your tests. But, that's one way to do it. So make sure you're, the same way as you would if you were memcopying in C. And make sure you're checking to know for sure you are dumping stuff in the right place and the memory is allocated correctly and all that business, right? So something to keep in mind. It's also very hard to undo. Very quick way to undo it is to fill whatever you just copied into with air blocks. So again, these present structure blocks. I wish. Well, actually, is structure blocks something new added in Minecraft? I really like. Do you mean like scaffolding? Absolutely. That is basically what memcopy is, right? And that's what clone is in essence, right? Oh my goodness, that's the coolest thing I've ever seen. I'm really not sure if it's in 1.15.2, which is the one we're using.
If it is, go for it. I can't say that I endorse it because I haven't used it.
Dude, yeah, I did not
But
know this was a thing. Man, I started playing like beta 1.8 when I was like small and my voice was still really high, higher than what it is now. So that's terrifying. But yes, if it works for you and it's compatible with this version of Minecraft, go for it. Although I've never used it, so if it causes any problems, you might be a little high and dry. Another thing is world edit, right? So the world edit mod improves upon clone commands features. It's a lot of stuff. It's street legal, I think. We're still working on confirming compatibility for it though, so make sure if it does kind of break your 389E mod, but the world is still openable, I'll take the time to grade it anyway. So that should be totally okay. You using world edit. So our goal is to make sure the world edit works at the end of the day. So you should be insured if you'd go ahead and use it. Right, do not try to use MC Edit unless you know exactly what you're doing. They dropped compatibility for our version of Minecraft 2 versions ago. I know it's easy to use MC Edit, but probably best not to mess with it. You'll get a lot of errors when you try to open your world. Unless somebody can prove me wrong, I don't know, I guess extra credit for that. That's really just out of the scope of this class. So if you can figure it out, awesome, great for you. But for the layperson, just go ahead and don't use MC Edit, right? It'll cause problems with your world. You don't want that. And that's all we've got. I know, Ashwath, I went a little over. If you want to talk a little bit about Project 3, that is all good.
Yeah, so Project 3 is going to be a multiplier circuit, just as very similar to what you saw in the diagrams today. It'll be, once you've done Project 2 with the adders, it should be like no problem at all once you figure out, like, the hardest part of this project is converting that circuit to something you can understand in Minecraft. Because you already know how to build adders and be familiar with it after P2. So it shouldn't be too bad. And the project description will have this is a 4x4. The one we want for the project is 3x3. So we have an updated one on the project description for Project 3, and that'll be out like very soon. Submission, just real quick. The mod is we've gotten submit working on the mod side, but there's some submit server kinks that need to be worked out, and for some reason It's very different from previous semesters when we've handled this, so I have to take this up the administrative chain, looks like. So we'll see. Probably P2 will be an submission unless I can magically get it working by tonight. But hopefully, as soon as possible, we will start using the test submit command.
Awesome. Yes, Ashwin's been hard at work on the submit server stuff. I wish I could tell you guys to give him a hand, but that would be really weird on Discord. I guess just send him like an emoji or something.
It's all good. I only deserve the praise if I can get it working.
Hey, no worries. But yes, that's kind of, I guess that's all we've got for today. Stick around for a teeny bit to answer questions. Extra credit quiz for today. Excellent reminder.
Oh, I'll make one. Yep.
Yes. Okay. Perfect. Yeah. No. Cool. So I guess that'll be up before end of day. You're all good there. Webcast as well will also be up in a day. I'm gonna go ahead and stop recording now.